From the first moment humans gazed at the star-filled night sky, we have been captivated by an insatiable desire to reach beyond our earthly bounds. Our story of interstellar dreams begins not in the modern era of rockets and space stations, but in ancient civilizations where storytellers wove tales of celestial journeys and cosmic adventures. Imagine yourself as a primitive human, standing beneath a pristine night sky untouched by light pollution, wondering what mysteries lie in those twinkling lights above. Throughout history, this primal fascination has driven us to push the boundaries of what is possible. The ancient Greeks imagined their gods traversing the cosmos, while Chinese astronomers mapped the heavens with incredible precision centuries before the telescope was invented. But it was not until the dawn of the 20th century that humanity's dreams of touching the stars began to crystallize into something more tangible. Enter the groundbreaking works of pioneers like Jules Verne and H.G. Wells, visionaries who dared to imagine what space travel might actually look like. Their stories did not just entertain. They planted seeds in the minds of generations to come. A young Wernher von Braun, who would later become one of the most influential rocket scientists in history, was profoundly inspired by Verne's From the Earth to the Moon. These works of fiction were not merely fantasies. They were blueprints for our collective future. The space race of the 1960s transformed these dreams into reality, but it also revealed just how challenging space travel would be. When Neil Armstrong set foot on the moon, he was not just making history. He was validating centuries of human imagination and scientific pursuit. Yet, even as we celebrated this monumental achievement, we realized that reaching our lunar neighbor was just the beginning. The vast emptiness between stars suddenly seemed more daunting than ever before. While we were focused on conquering the moon, something extraordinary was happening in laboratories and universities across the globe. Scientists began discovering phenomena that seemed to defy our understanding of physics itself. Quantum entanglement, dark energy, and the possibility of higher dimensions. These discoveries suggested that the universe might be stranger and more accommodating to interstellar travel than we ever imagined. Consider this: right now, as you read these words, there are particles in your body that exist in multiple places simultaneously, thanks to quantum mechanics. This same principle might one day be the key to crossing the vast distances between stars. The physics that makes your smartphone work, technology that would seem like magic to someone from just a century ago, hints at possibilities we are only beginning to understand. The story of our interstellar dreams is not just about technology. It is about evolution. Humanity has consistently proven that what seems impossible in one era becomes commonplace in the next. When the Wright brothers first flew at Kitty Hawk, their journey lasted just 12 seconds. 66 years later, we were walking on the moon. This exponential pace of progress is not slowing down. It is accelerating. Picture this. Deep in the Nevada desert, scientists are currently working on experiments that could fundamentally alter our understanding of space-time. They are investigating theories suggesting that the fabric of space itself might be manipulated, creating shortcuts through the cosmos. While this sounds like science fiction, so did the concept of instant global communication just a few generations ago. But here is the truly mind-bending part. We might not be alone in this pursuit. For decades, astronomers have been detecting increasingly bizarre phenomena in deep space, objects and energy patterns that do not fit our current models of physics. Some scientists have begun to wonder if these anomalies might be evidence of advanced civilizations that have already solved the puzzle of interstellar travel. Imagine if tomorrow we discovered that what we thought were natural astronomical phenomena were actually the remnants of ancient space highways, built by civilizations that mastered interstellar travel millions of years ago. The technology might be sitting right in front of us, hidden in plain sight, waiting for us to reach the right level of understanding to recognize it. As we delve deeper into quantum physics and our understanding of the universe expands, we are beginning to realize that space and time might not be the rigid barriers we once thought they were. The same equations that Einstein used to prove the impossibility of faster-than-light travel might actually contain loopholes that make interstellar travel not just possible, but inevitable. This brings us to a startling possibility. What if our current understanding of physics is as primitive compared to what is actually possible as stone tools were to modern technology? What if the true nature of space travel is not about building bigger rockets or more powerful engines, but about understanding the fundamental fabric of reality itself. Recent breakthroughs in quantum computing and artificial intelligence are beginning to suggest that consciousness itself might play a role in how the universe operates. Some theoretical physicists now propose that human consciousness could be the key to unlocking interstellar travel, not through traditional means, but through ways we can barely comprehend with our current level of understanding. As we stand on the brink of these discoveries, looking up at the same stars that captivated our ancestors, we are beginning to realize that our journey to the stars might not be just about crossing physical distance. It might be about transcending our current understanding of what is possible, about evolving not just technologically, but as a species. The real question is not whether interstellar travel will be possible, but whether we are ready for what we will discover when we finally achieve it. But there is something even more extraordinary brewing in laboratories of the world's most advanced research facilities. Recent classified experiments have begun to show patterns that suggest we might have been thinking about space travel all wrong. These findings are so revolutionary that they challenge not just our understanding of physics, but our very concept of reality itself. And the most shocking part? The evidence suggests that the key to interstellar travel might have been within us all along, hidden in the very structure of human consciousness. As we venture into the stark reality of interstellar travel, the challenges that lie ahead are as vast as space itself. Imagine standing at the edge of the Pacific Ocean with nothing but a rowboat. That is essentially where we are in terms of our current technological capabilities for interstellar travel. The distances involved are so immense that they stretch not just our technological capabilities, but our very understanding of what is possible. Consider this: the nearest star system to Earth, Alpha Centauri, lies about 4.37 light-years away. To put this in perspective, light, the fastest thing in the universe, takes more than 4 years to reach it, traveling at an astonishing speed of 299,792 kilometers per second. Our fastest spacecraft to date, the Parker Solar Probe, reaches speeds of about 430 kilometers per second at its fastest. At this rate, it would take nearly 7,000 years to reach our nearest stellar neighbor. But the problem of distance is just the beginning of our challenges. The human body, evolved for life on Earth, faces severe limitations in space. Extended periods in zero gravity cause muscle atrophy, bone density loss, and potential brain changes. Our astronauts on the International Space Station already experienced these issues during their relatively short stays. Now imagine these effects multiplied over decades or even centuries of space travel. The technological hurdles we face are equally daunting. Current rocket technology relies on chemical propulsion, essentially controlled explosions that push spacecraft forward. While this works for reaching orbit or even the moon, it is woefully inadequate for interstellar travel. The amount of fuel required for such journeys would be astronomical, quite literally. The rocket equation shows us that the longer the journey, the more fuel we need, but the more fuel we carry, the heavier our spacecraft becomes, requiring even more fuel to move it. Radiation presents another formidable challenge. Earth's magnetic field and atmosphere protect us from deadly cosmic radiation, but in deep space, this protection disappears. The radiation exposure during a journey to Mars alone would be significant. Now multiply that by thousands for an interstellar journey. Current shielding technology is heavy and only partially effective, and we haven't yet developed materials that can provide adequate protection for such extended periods. The question of resources becomes critical when we consider long-term space travel. Every gram of water, every molecule of oxygen, every morsel of food must be either carried along or generated during the journey. Current life support systems require regular maintenance and replacement parts. The complexity of creating a truly closed, self-sustaining system that can operate reliably for decades or centuries is mind-boggling. Time itself becomes a cruel adversary in interstellar travel. Even if we could achieve speeds of 10% the speed of light, which is far beyond our current capabilities, it would still take over 40 years to reach Alpha Centauri. This raises profound questions about crew selection and generational ships. Would we send young adults who might spend their entire lives in transit? Would children be born and raised in space, never knowing Earth except through recordings and stories? The psychological challenges are equally daunting. How do we prepare humans for the profound isolation of deep space? The Earth would eventually appear as just another star in the sky. Communications would face increasing delays. At some point, a simple message exchange could take years. The psychological impact of such isolation, combined with the knowledge that Earth and everyone you know is unreachable, presents unprecedented challenges for human psychology. The engineering challenges extend to every aspect of spacecraft design. Materials must withstand decades of micro-impacts from space dust, extreme temperature variations, and the constant stress of operation. Computer systems must function reliably for generations without external support or replacement parts. Every component must be either incredibly durable or easily replaceable with limited resources. Energy management presents another crucial challenge. Solar power becomes impractical as ships move away from stars, and nuclear power, while promising, presents its own set of challenges in terms of fuel supply, waste management, and safety over extremely long periods. The energy required for life support systems, propulsion, and maintaining essential spacecraft functions over decades or centuries is staggering. The problem of navigation in interstellar space is more complex than most people realize. While stars may seem fixed from Earth, they're actually moving through space at various velocities. Plotting a course through three-dimensional space, accounting for gravitational influences, and maintaining precise trajectory control over years or decades requires computational capabilities far beyond what we currently possess. Even if we solve all these technical challenges, we face the problem of deceleration. It's not enough to reach another star system. We need to be able to slow down when we get there. The energy required for deceleration is roughly equal to that needed for acceleration, effectively doubling our propulsion challenges. The economic costs of interstellar travel are almost incomprehensible. The resources required would dwarf anything humanity has ever attempted. The development of necessary technologies, construction of spacecraft, and support infrastructure would require global cooperation on an unprecedented scale. Even with projected economic growth, the cost of interstellar missions might exceed the entire global GDP of Earth. Then there's the challenge of redundancy and repair. Any system critical to survival would need multiple backups, increasing the complexity and mass of the spacecraft. The ability to manufacture replacement parts during the journey becomes essential, requiring sophisticated three-dimensional printing and manufacturing capabilities in space. We're also facing the challenge of information management. The knowledge required to maintain and repair all systems would be vast, requiring highly sophisticated artificial intelligence systems or an extensive crew of specialists. Either option presents its own set of challenges in terms of reliability, training, and long-term sustainability. The problem of maintaining genetic diversity in a small population over multiple generations poses another significant challenge. If we're sending humans on multi-generational journeys, we need to ensure the population remains viable and healthy over many generations of isolation. Recent experiments in closed ecosystems have shown just how difficult it is to create self-sustaining biological systems. Projects have revealed numerous unexpected challenges in maintaining stable ecosystems, and these were just on Earth. Creating and maintaining such systems in space, over generations, adds layers of complexity we're only beginning to understand. The development of artificial gravity systems presents another significant technical hurdle. While rotating sections of spacecraft could theoretically provide artificial gravity, the engineering challenges of building and maintaining such systems over decades of operation are immense. The size required for comfortable human habitation while avoiding problematic side effects like motion sickness adds considerable complexity to spacecraft design. The question of preserving human health over multiple generations in space remains largely unanswered. We're still discovering new ways that space affects the human body, from changes in gene expression to alterations in brain function. Long-term exposure to reduced gravity environments might have effects we haven't even anticipated yet. But perhaps the most sobering challenge is the sheer scale of what we're attempting. The distances involved in interstellar travel are so vast that they're difficult for the human mind to comprehend. Every system, every component, every biological and technological process must function nearly perfectly for decades or centuries, a level of reliability far beyond anything we've achieved in human engineering. As our understanding of these challenges deepens, scientists have begun to uncover something even more unsettling. Recent theoretical work suggests that there might be fundamental limits to technological advancement that we're approaching, limits that could make conventional interstellar travel physically impossible. This revelation has led some researchers to propose that if interstellar travel is possible at all, it must operate on principles that completely contradict our current understanding of physics. And the evidence for this might be hiding in a series of anomalous experimental results that no one has been able to explain. Emerging technologies and revolutionary concepts stand at the frontier of humanity's greatest adventure. In the sprawling research facilities of leading space agencies and private aerospace companies, scientists and engineers are quietly working on technologies that would seem like magic to our grandparents. These innovations aren't just incremental improvements. They represent quantum leaps in our understanding of what's possible. Deep within the laboratories of quantum physicists, a revolutionary concept is taking shape: quantum vacuum thrusters. These devices, which harness the bizarre properties of quantum mechanics, could potentially create propulsion by manipulating the very fabric of space-time. Early prototypes have shown mysterious forces that defy conventional physics, leading some scientists to believe we're on the verge of a propulsion breakthrough as significant as the jump from steam engines to nuclear power. The concept of space-time manipulation has moved from science fiction into serious scientific discourse. Advanced theoretical models suggest that space isn't the rigid container we once imagined, but rather a flexible medium that could potentially be warped and folded. Scientists working on cutting-edge experiments have begun detecting minute anomalies that hint at the possibility of localized space-time distortions. While these effects are currently microscopic, they represent the first experimental evidence that space-time might be manipulated under the right conditions. Antimatter propulsion, once relegated to the realm of science fiction, is now being seriously developed in particle physics laboratories. The energy released when matter and antimatter annihilate each other is orders of magnitude greater than nuclear fusion. Recent breakthroughs in antimatter production and containment have reduced the cost of creating antimatter by a factor of thousands. While still prohibitively expensive for large-scale use, the trend suggests that antimatter-based propulsion systems might become viable within decades. But perhaps the most promising development lies in the field of quantum entanglement. Scientists have recently discovered that entangled particles might be able to transmit information and potentially energy instantaneously across any distance. This phenomenon, which Einstein famously called spooky action at a distance, could be the key to developing faster-than-light communication systems. Some theoretical physicists propose that this same principle might be extended to create quantum tunnels through spacetime itself. Artificial hibernation technology has made remarkable progress. Research teams have successfully induced and maintained suspended animation in larger mammals for increasingly extended periods. This technology, combined with advanced life support systems, could solve many of the biological challenges of long-term space travel. Imagine crews spending decades in carefully controlled hibernation, their aging processes slowed to a crawl, while automated systems guide their vessel between the stars. Breakthrough Starshot, a real-world project backed by some of the world's leading scientists and entrepreneurs, is developing revolutionary light sail technology. By using powerful ground-based lasers to accelerate tiny spacecraft to unprecedented speeds, they aim to reach Alpha Centauri within decades rather than millennia. While currently designed for unmanned probes, the principles could potentially be scaled up for larger vessels. The development of self-replicating machines, once considered purely theoretical, is now progressing in unexpected ways. These machines, based on advanced 3D printing technology and artificial intelligence, could potentially construct entire space stations and spacecraft using raw materials found in asteroid belts and on other planets. This technology could create a network of refueling and repair stations throughout our solar system, serving as stepping stones to the stars. Artificial intelligence has evolved far beyond simple computational tasks. Modern AI systems are beginning to demonstrate creative problem-solving abilities that match or exceed human capabilities in specific domains. These systems could potentially manage the complex calculations required for interstellar navigation and make split-second decisions that would be impossible for human crews. Some scientists propose that future spacecraft might be guided by artificial intelligence so sophisticated it borders on consciousness. Advanced fusion technology, while still in development, shows incredible promise. The recent breakthroughs in controlling plasma containment have brought us closer than ever to achieving sustainable fusion reactions. This technology could provide the massive amounts of energy required for interstellar travel while being far more efficient than current propulsion systems. Scientists working on exotic matter research have made unexpected discoveries about the nature of negative energy densities, a crucial component for many theoretical faster-than-light travel concepts. While creating exotic matter with negative mass remains challenging, new approaches using quantum field theory have suggested possible pathways to manipulate matter in ways previously thought impossible. The development of metamaterials has opened up entirely new possibilities in spacecraft design. These engineered materials exhibit properties not found in nature, such as the ability to redirect electromagnetic radiation or convert one form of energy into another with unprecedented efficiency. Some theoretical models suggest that certain configurations of metamaterials might be able to create localized distortions in spacetime. Biological engineering advances have created organisms capable of surviving in extreme environments. Scientists are now working on developing biological systems that could form part of spacecraft life support systems, creating self-sustaining ecosystems that could support human life indefinitely. These bioengineered systems could solve many of the resource management challenges of long-term space travel. The concept of quantum slipstream technology, while still theoretical, has gained serious attention from mainstream physics. This approach suggests that quantum-level manipulation of spacetime could create temporary corridors through space where normal physical laws are altered, potentially allowing faster-than-light travel without violating Einstein's theories. However, hidden within these groundbreaking developments lies a disturbing pattern that few have noticed. As our understanding of these technologies deepens, some scientists have begun to suspect that we're not the first civilization to pursue these solutions. Strange anomalies in our experimental data suggest that someone or something might have already mastered these technologies, leaving subtle traces throughout our universe. Even more unsettling, recent calculations suggest that if this hypothesis is correct, we might be about to make contact with them, whether we're ready or not.